Okay, everyone, welcome back to our Calculus 3 class notes. We are now on page, 102, right? No, 103. And we're in section 15.7, and we are talking about doing triple integrals in different coordinate systems other than rectangular. So we talked about cylindrical, and now we're going to talk about spherical. For spherical coordinates, what we do is we imagine these coordinates come from a system where it makes more sense to think about spheres. Okay, so they represent a point P in space by ordered triples, which are rho, the angles phi and theta. Okay, so that same point can be represented as x, y, z, of course, or as r, theta, and z, which is cylindrical coordinates, or as rho, phi, and theta. Now, rho is the distance from the origin to the point, the straight distance from it, not its shadow down on the xy plane, because that's what r is. And then phi is the angle measured from the positive z-axis. So it's down from the positive z-axis to the ray that gives us rho, which is the distance out to the point. And then theta is the same angle theta that we use in the cylindrical coordinate system. So the shadow of the point down onto the xy plane, the angle theta is the angle measured from the positive x-axis over to the ray that would give us r in the cylindrical coordinate system. Now the equations relating spherical coordinates to Cartesian and cylindrical coordinates are this. So r is rho sine phi and z is rho cosine phi. Theta stays theta because it's the same in both cylindrical and spherical. X, of course, is r cosine theta, which means r is rho sine phi times theta is cosine theta. So you can put it all in terms. You can put them in terms of cylindrical coordinates or in terms of the spherical coordinates. And y is r sine theta in cylindrical, which is thus rho sine of phi sine of theta in spherical coordinates. And rho is equal to the square root of x squared plus y squared plus z squared, or the square root of r squared plus z squared. Now, the dv, which was dz dy dx in rectangular coordinates, or dz r dr d theta in cylindrical coordinates, is now rho squared sine of phi d rho d phi d theta. Okay, so how would I use that? I want to find the volume of the ice cream cone d cut from the solid sphere. Rho is less than 1, so that would be a ball that went all the way around and filled in. But the ice cream cone, I'm going to cut it by the cone phi equals pi over 3. So notice that's a really nice way to describe a cone. It just says the angle made with from the positive z-axis down is pi over 3. And then rho and theta can be anything, so it circles all the way around. And then we're cutting it at rho equals 1, so it gives this ice cream cone look here. That makes a really simple integral. If I want the volume of such a thing, and I do it in terms of spherical coordinates, then I'm going to integrate rho from 0 to 1 to cover the whole ice cream cone. Phi is going to go from 0 down to pi over 3 to get that whole ice cream cone. And theta will wrap itself all the way around from 0 to 2 pi. And this just becomes very simple integrals then. First I integrate respect to rho. I get rho cubed over 3, evaluated from rho equals 0 to rho equals 1 to get a third. I'm going to pull out the 1/3. Then I'm going to integrate sine of phi, which is minus cosine of phi. I'll pull out the minus sign so I don't have to deal with it. Evaluate that from phi equals 0 to phi equals pi over 3. So I get cosine of pi over 3, which is a half, minus cosine of 0, which is 1. So this becomes minus a half. Pull out the minus a half, I get 1/6. Integrate d theta from 0 to 2 pi. So I get theta, evaluate from 0 to 2 pi, I just get 2 pi over 6 or pi over 3 cubic units.